Hello everyone, welcome back, and in today's video we're going to be discussing a problem that appeared in IIT 1993, and this question is based on the concepts from geometrical and wave optics. So give this problem a try for a few minutes and then come back for the solution. So let's read the problem statement. So in the given figure, S is a monochromatic point source that is emitting light of wavelength 500 nanometer. A thin lens of circular shape and focal length of 0.1 meter is cut into two identical halves, L1 and L2, by a plane passing through a diameter. The two halves are placed symmetrically about the central axis SO with a gap of 0.5 meters. The distance along the axis from S to L1 and L2 is 0.15 meters, while that from L1 to L2 is 1.3 meters. The screen at O is normal to SO. In the first question, they're asking if the third intensity maximum occurs at the point A on the screen, find the distance OA. So apparently some fringes are being formed on the screen over here, and we have to find the distance of the third maxima from the point O. Okay, first let's try to figure out where will the images of the source be formed. Okay, so what they did is they cut the lens from at its midpoint over here, and then they separated out each of the halves by a distance of 0.25 mm. Okay, so then we have to first figure out where the images will be formed. Okay guys, so this is basically how the setup is looking like. Now, so let's name the upper lens as L1 and let's name this bottom half as L2. So initially the optical axis of this upper lens was over here, right? And now it is displaced upwards by an amount of 0.25 mm from our original axis. So I'm going to mark that new optical axis with some dotted lines. And first let's figure out where the image due to lens L1 will be formed. Now the object distance is given to be 0.15 meters. Now using the lens formula, we can find distance of the image from our lens, and it comes out to be 0.3 meters after calculations. Okay. But now as the optical axis is shifted, the object height HO is now equal to 0.25 mm. So now let's determine the magnification. So M is simply equal to V divided by U, which comes out to be -2, which basically means the image height is going to be, first of all, twice the height of the object, and it will be inverted. Okay, so if I have to finally mark out where the image is going to be, firstly it's going to be at a distance of 0.3 meters from the lens, and its height will be 2 times of 0.25, that is 0.5 mm from the optical axis. So this is where our image due to lens 1 will be formed, and its height from the optical axis is again 0.5 mm. Now by symmetry, we can say that the image due to L2, similarly, we formed at a distance of 0.5 mm from the optical axis of L2, right? Okay, so let's mark that as well. So if this is the optical axis, the image I2 will be formed again at a distance of 0.5 mm from the optical axis. And the distance between their optical axes is again 0.5 mm. So after refraction from the lenses, the images are formed at firstly a distance of 0.3 mm from the lenses, and they are separated by a distance of 1.5 mm. Okay, so let's now draw it in a different page. Okay, so now these individual images, that is I1 and I2, will act as independent sources emitting light, and as a result of which we'll observe interference pattern on the screen over here. So the distance between the lens and the screen was 1.3 meter, which means the distance from the image and the screen is going to be 1 meter. Now using the common results from the YDSC experiment, the fringe with beta is actually lambda capital D by small d, where capital D is the distance between the screen and the slit plane, and small d is the separation between the slits or the sources in this case. So this comes out to be, so this after calculation comes out to be 1 by 3 times 10 to the power minus 3 meters. So in the first question, they required us to find the distance of the third intensity maximum. Okay. So basically, first of all, the central maxima will be formed at the point O. Then we know the first maxima will be formed at a distance of beta. So similarly, the third maxima will be formed at a distance of 3 beta from the point O. So our answer to A option is simply going to be 3 beta, which is equal to 10 power minus 3 meters. Meters, or simply 1 millimeter. Okay. And in the second question, they're saying if the gap between L1 and L2 is reduced from its original value of 0.5 mm, will the distance OA increase, decrease, or remain the same? Okay, so will the fringe width change or not is what they're asking. So let's go to page 2. So here, if the separation between these lenses is reduced, then we can clearly say that the separation between the images will also be reduced. So essentially what we're saying is that the value of small d is gonna decrease, which basically means the fringe width is gonna increase. And therefore the distance of the third maxima, or the distance of any maxima from the point O, will increase. So the answer for option B is that the distance will increase. So that was it for this video, guys. If you have any doubts, you can comment down below, and do like and subscribe to the channel if you enjoyed the video, and thanks for watching.